conservation of angular momentum. Conservation of angular momentum. See here, statement. When no external torque acts on the body, then angular momentum of the body is conserved. This is our statement. That means if tau is equal to 0, then EL is equal to constant, or I omega is equal to constant. This is our statement. Now we have to prove this. Suppose we consider proof. We know tau is equal to I alpha. Therefore, I will write here tau is equal to I into, suppose this is equation number 1, d omega by dt, and therefore torque is equal to d dt of I omega, and therefore torque is equal to dl by dt. Suppose equation number 2. Now, if tau is equal to 0, then dl by dt is equal to 0, and therefore L is equal to constant, or I omega is equal to constant. This is our proof. Now here we consider, suppose a ballet dancer on his table. This table is rotating, and suppose on this table a ballet dancer is there. Suppose this is the block diagram. We consider these hands are outstretched, and suppose I1 be the moment of inertia, omega 1 be the velocity, and whenever these hands are, we consider next. Suppose same thing. This is the block diagram. Try to understand. Suppose these hands are folded. I2 be the moment of inertia, omega 2 be the velocity. Then here you see I1 omega 1. This is the product. I2 omega 2. This is the product. And this product comes out to be constant. That means if I1 decreases, then omega 1 increases. If I1 increases, omega 1 decreases. Similarly, I2 decreases, omega 2 increases. I2 increases, omega 2 decreases. Like that. That means whenever moment of inertia decreases, angular velocity increases. Moment of inertia increases, then moment of inertia decreases. Like that. This is all about the conservation of angular momentum. Now we consider next article. Moment of inertia and torque. See here, suppose you consider a body of any shape. Suppose this is the axis of rotation. Suppose you consider number of masses m1, m2, m3, m4, mn. Suppose these masses are distances r1, r2, r3, r4, rn. Suppose f1 force on first, f2 force on second, f3 force on third, f4 force on fourth, fn force on n particle. Then here suppose you consider m1, m2, m3, f2, mn be the masses, r1, r2, r3, rn be the distances, f1, f2, f3, f2, fn be the forces, a1, a2, a3 up to an. These are the accelerations on n particles. Then here we can write here, that is a1 is equal to r1 alpha. Then a2 is equal to, I can write r2 alpha. Alpha with the angular acceleration. Alpha, this is the angular acceleration. Similarly, an is equal to Rn alpha, and therefore I will write here F1 force. F1 is equal to M1 A1, therefore M1 R1 alpha. Similarly, F2 is equal to, I can write M2 R2 alpha, like that. Fn is equal to Mn Rn alpha. Suppose these are equation number 1, these are equation number 2. Now torque is equal to force into moment arm, and therefore I will write torque to1 is equal to F1 R1, which is equal to F1 M1 R1 alpha into R1 is equal to M1 R1 square alpha. To2 is equal to, similarly we can write M2 R2 square alpha, like that. To n is equal to Mn Rn alpha. Suppose all these are equation number 3. And total torque tau is equal to, I can write tau 1 plus tau 2 plus up to tau n. Suppose equation number 4. And therefore torque is equal to, I will put all the values from equation 3 in equation 4. Torque is equal to M1 R1 square alpha plus M2 R2 square alpha plus Mn Rn square alpha is equal to M1 R1 square plus M2 R2 square plus Mn Rn square alpha, which is equal to, I will write here summation Mi Ri square I equal to 1 to n into alpha, and tau is equal to, therefore torque is equal to, we can write here, this quantity is I, means I alpha. Suppose equation number 4. This is relation between moment of inertia and torque. Again here you see F is equal to M into A. See here, force analogous with torque, linear acceleration analogous with angular acceleration, and mass analogous with moment of inertia. Therefore again here we have proved moment of inertia is nothing but mass in rotational motion. Here we complete the chapter 1, that is rotational dynamics. Thank you. Now we consider here in the same, that is lecture number 11. Lecture number 11, examples. See here, suppose we consider example number 10. Sorry, example number we consider, that is page number 24. In that example number 12, I think, somehow an ant is stuck to a rim of a bicycle wheel of diameter 1 millimeter, while the bicycle is on a central stand. Bicycle is on the central stand, the wheel is set into rotation, and it attains the frequency 2 revolution per second in 10 seconds with uniform angular acceleration. Calculate number of revolutions completed by the ant in these 10 seconds, time taken by it for first complete revolution and last complete revolution. This is our example number 12. Now here you have given small d equal to 1 meter, then small r is equal to 0.5 meter, then n equal to 2 revolution per second, and therefore omega is equal to 2 pi n is equal to 12.56 radian per second. T is equal to 10 second. This is given. Now here first we will consider, that is theta is equal to omega 0 t plus half alpha t square. Omega is equal to omega 0 plus alpha t. Omega is equal to 0 plus alpha t. Here we have to first calculate alpha. Theta is equal to omega 0 t plus half alpha t square. Therefore theta is equal to, we get here first we will calculate this alpha. Therefore alpha is equal to omega upon t is equal to 12.56 divided by 10 means 1.256. And now put this value here. Theta is equal to, we get here half into 1.256 into t square means 100. And if we calculate all these, we get here 62.8 radian. And number of revolutions is equal to theta upon 2 pi. We get here 62.8 divided by 6.28 means 10 revolutions. This is our first answer. Now, secondly, for first revolution, theta is equal to omega 0 t plus half alpha t square. We have calculated this. That is, we get here 2 pi is equal to 0 plus half into 1.256 into t square. 6.28 is equal to 0.628 into t square, and therefore t square is equal to 6.28 divided by 0.628 means 10, and therefore t is equal to root 10 second. For last revolution, theta is equal to omega 0 t1 plus half alpha t1 square. 18 pi is equal to 0 plus half into 1.256 into t1 square. And if we calculate all these, then we get here t1 is equal to 3 root 10 second. Now we calculate t dash. T dash is equal to 10 minus 3 root 10, which comes out to be 0.51 second. This is example number 12. Now we consider next example number 13. Coefficient of static friction between a coin and rectangular coin and a gramophone disc is 0.5. Radius of the disc is 8 cm. Initially, the center of coin is 5 cm away from the center of the disc. At what minimum frequency will it start slipping from there? By what fraction will the answer change if the coin is almost at the rim? Small g equal to pi square you have given. Here you see, mu s is equal to 0.5. Capital R is equal to 8 cm means 0.08 meter. Small r is equal to pi cm means 0.01 pi meter. Here we write mu s into mg is equal to mr omega square. This m gets cancelled. Omega square is equal to, we get here mu s into small g divided by r. We put the values. 4 pi square into n square is equal to 0.5 into pi square divided by 0.01 pi. Here pi square gets cancelled, and if we solve all these, we get here n square is equal to 3.98, nearly equal to 4, and therefore n is equal to 2 revolution per second. Now we consider secondly, that is mu s mg, same thing, omega square equal to mu s small g upon capital R. And if we put all the values, then 4 pi square n square is equal to 0.5 pi square divided by, here we consider 0.08, and if we calculate this all, then we get here, suppose this is n1 is equal to 1.25. This is our answer. Thank you.